What's up, dudes? It's Joshua, and welcome back to another Physics 2211 Lab 3 presentation. Now, this one is on black holes and orbits, and in this lab, I explored the gravitational dynamics, first using a star orbiting a black hole, and then simulating a three-body system with a planet, moon, and a spaceship. Now, this lab has two main goals. The first is to determine the mass of the black hole by studying the orbit of the nearby star, and the second is to simulate a spaceship interacting gravitationally with a planet and its moon and try to get a stable figure eight orbit. To solve both of these parts, we applied Newton's laws, specifically Newton's second law, which links force to motion, and the universal law of gravitation that tells us how mass and distance affect a gravitational pull. By using these, we can calculate how objects move throughout space. To simplify the simulations, we assumed gravity was the only force acting on the system, everything was a point mass, and the systems were isolated. Using those assumptions, I calculated that the black hole's mass is about 1.98 times 10 to the 34th of kilograms, and found that the initial velocity of the spaceship should be negative 25,000 in the x direction and 25,000 in the y direction meters per second. Part 1, I used the momentum principle to determine the gravitational force on the star. I used the change in momentum over time to find the net force and applied that to estimate the black hole's mass. And as you can see before, I estimate the black hole's mass to be about 2 times 10 to the 34 kilograms. Now, in the three-body simulation, I set up a planet, a moon, and a spaceship all interacting with each other and through gravity. The spaceship starts with a high initial velocity so it can interact with both bodies without crashing into either one. The spaceship is considered the quote-unquote system, and the planet and the moon provide all the gravitational forces. At every time step, I calculated the gravitational pull from both objects to update the ship's momentum and position. The results I got from part two is not a stable figure eight, but it was a success because there's no collision with the spaceship, with the moon, or planet. Some errors come from the simplified physics and numerical methods that we used, using a smaller time step, better initial conditions, and maybe possibly relativistic effects could improve the accuracy and realism of the simulation. Now, what does it mean? The net force acting on the spaceship is the sum of the gravitational forces exerted by both the moon and the planet. Similarly, the moon experiences a net force due to the planet's gravity. The parallel component of a force describes how the magnitude of momentum changes for each object. This affects how their speed increases or decreases, and the perpendicular component is responsible for changing only the direction of the object's motion. This component plays the role of shaping the spaceship's trajectory, and that makes the looping or figure eight path when it's set correctly. Now, what if the imaginary system has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? We would now need to include the force that acts on the star, the planet, and the moon from the black hole. To predict how everything moves, we'd have to include the black hole's gravity in our model. Since black holes are incredibly strong, they could completely mess up the normal orbits of the star, planet, and the moon. And in the worst case scenario, the black hole could pull all of them in and destroy them, spaghettifying, if you will, the entire system. To figure out the paths of each object, we need the black hole's mass and its distance from each body in the system.